Thank you everyone for joining today. We are very excited to host a brilliant and noteworthy astrophysicist from Bristol University, Professor Mark Birkinshaw. Professor Birkinshaw research focuses in the fields of cosmology, on the large-scale structure of the universe and how it changes, and on the astrophysics side concentrates on the properties of the huge black holes at the centers of galaxies, mainly on their fast flows and their effect on their surroundings, using both observation and theory. He has received his bachelor's degree from the Cambridge University. I'm going to mention the date, and his PhD from Cambridge University as well, and later on has been awarded a prestigious Alfred Sloan Research Fellowship. Professor Birkinshaw is particularly known for making the first detections of the change in the brightness of the microwave background radiation caused by inverse-Compton scattering in clusters of galaxies, the also known Sunyaev-Zel'dovich effect, and in demonstrating how this effect can be used to measure cosmological parameters. He has worked on NASA's Chandra satellite before its launch, and along with other space-based and ground-based telescopes from X-ray to optical to radio bands, he studies galaxies, especially those hosting massive black holes and showing signs of unusual activity. Professor Birkinshaw has held a number of positions, which I cannot even enumerate now, from Berkeley University to Cambridge to CFA, and now being in holding the position at Bristol University since 1995. To wrap up, he also gives professional and public presentations in all these areas, but he also speaks and writes on more general astronomical and cosmological topics. So many thanks, and I'll leave the stage to you. Many thanks, Mark.
Okay, thanks, Konstantinos. This is going to be a bit of a grab bag of things based on some recent radio mapping that I've been doing to follow up on some work we did on a southern Abell cluster, which will be in a very good part of the sky for Meerkat. Collaborators very much happy to have on board, and also for SKA when it comes around. So let's get moving, if I can persuade this thing to talk to me. So I'm going to touch on 4 cases, one in some depth, one slightly more depth, and a couple very briefly. I'm going to concentrate on the cluster Abell 3744, which is a relatively low redshift southern cluster, which has 3 nice bright NGC galaxies at its center, and has some curious radio features that I think are worthy of note. I'll then talk a little bit about the work we've been doing looking for binary supermassive black holes in a couple of brightest cluster galaxies, those of Abell 85 and Abell 1775. And I'll show a recent map made by one of my graduate students, Emmanuel Bempon-Manful, on 3C83.1b, showing, as if it needed reinforcement, why LOFAR can give you some extra information about the energetics that radio galaxies feed back into the intercluster medium. So why do I care about this? Well, principally because of feedback processes. We know that clusters of galaxies and many groups are relatively strong X-ray emitters. That means that their intergalactic material is losing thermal energy fairly rapidly and therefore losing pressure, and so should be drifting inwards towards the bottoms of the gravitational potential wells. If they're not going to have collapsed completely over about 10 to the 9 years, there's got to be some heating source within the clusters. And that heating source has got to be regulated. If it was unregulated, it could be inadequate to counter the flow. If it was excessive, then it could blow the atmospheres completely away. And as Konstantinos well knows, that's one of the things that may be affecting small groups of galaxies in very great numbers. The most obvious heating source is an active galaxy somewhere near the center of the cluster material. But it's not entirely clear how active galaxies do the heating and how the regulation process happens. Most likely it's a sporadic process, and some sort of time average heating is what's really going on. Though with only a limited number of billions of years since clusters started forming, it's unlikely that individual outburst events have smoothed out to give a uniform cluster structure. You would expect to see the imprints of multiple thermal pulses. I'm also interested in how that same heating process can cause magnetization of the intercluster medium. If the radioplasma is coming out and doing work, it's going to be carrying along with it relativistic particles and magnetic fields. And the question about where those fields end up and how they're recycled by turbulence in the intercluster medium into higher field strengths and also into stochastic acceleration of particles is an interesting question. And finally, if part of the regulation process involves gravitational collapse, you would expect a heightened rate of galaxy mergers during the periods immediately before radio outbursts. And so we might be able to find supermassive black hole binaries associated with brightest cluster galaxies where some heating feedback is currently going on. So that's the motivation for the stories I'm going to be showing. Just a reminder about some numbers. The sorts of gas temperatures we're talking about are in the range 1 to 10 keV, and that's X-ray language, or 10 to the 7 to 10 to the 8 Kelvin in physicist language. The gas densities are around about 10 to the 2 to 10 to the 3 particles per cubic meter. And for those of you who are CGS obsessed, that's around about 10 to the -4 to 10 to the -3 per cubic centimeter. We have strong X-ray emission because this means that n squared t to the half, which is proportional to the emission measure, is quite a large number. But the gas we're talking about is intrinsically collisionless. The mean free paths of particles are of order 10 to the 25 meters. And we only see the gas acting as a gas because of the effects of embedded magnetic fields that cause the gyro radii of particles to be quite small. The typical gyro radius of a proton is around 1000 AU, even in the sort of gas that we're talking about here, which is substantially less than the sorts of scales that we normally image. So let's get on to Abell 3744. Why are we looking at this thing? The main reason is that when we were trying to find places where there was likely very strong magnetization and heating, we looked for dense clusters with significant X-ray emission, where there was also evidence of an unusually structured radio source. And Abell 3744 came top of the list. There was existing information showing that there was something funny going on in there, and it was going to be possible to get rather good X-ray data. It's close enough that there's a lot of archival galaxy dynamical information, so we can look at how the galaxies are distributed quite nicely as well. So we took this on as a simplish project, which has now dragged on for rather a lot of years because it's yielded rather more information and rather more difficult information than we thought we'd get. Here's the obligatory optical picture of the cluster. There are a number of bright galaxies in the cluster core region. The most spherical of them is NGC 7016. To its southeast is NGC 7017, which is utterly boring. And to its northeast is NGC 7018. The redshift is about 0.0377. That's based on an average of 56 galaxies. And the velocity dispersion along the line of sight is about 350 kilometers per second. I remind you that this is round about a third the velocity dispersion of something like the Perseus cluster. So it's an unimpressive velocity dispersion, and it implies that the temperature of the gas is going to be relatively low. That's good for high quality imaging because it implies there'll be lots of counts in the passband of something like the Chandra satellite. I did a tree analysis of the galaxy positions in phase space for the cluster and found that the dominant cluster is indeed at a redshift 0.0377, but there's evidence of several distinct subgroups with velocities of up to a couple of thousand kilometers per second relative to the main cluster, containing of order 5 or maybe 10 members, which are presumably infalling. So this is a cluster that is probably not settled down in any real sense yet. So again, a place where we might expect mergers and some interesting dynamics to be going on. This was the radio map that got us started. This covers the entire cluster. This is about a 1.5 megaparsec square field from the VLA Sky Survey. You can see something that looks a bit like a squashed slug at the middle of the field, a radio source to the northeast, which is probably unrelated, and structure in there that needs some interpretation. The declination is about -25.5 degrees, so very well placed for those of you in South Africa. The best archival data set I could find on the cluster is shown here. This is at 1.4 gigahertz. The beam is about 13.5 arc seconds in full width half maximum, corresponding to about 10 kiloparsecs. The crosses on the image show the locations in NGC 7016, 7017, 7018. What we see is something that looks like a classic 3C465 type galaxy associated with 3C with NGC 7018, a bent double of some kind. We see a trail-like source associated with NGC 7016, and 7017 may or may not be a radio source, you can't tell. It's superimposed on the trail. Based on that image, what we could say was that 7016 is definitely two-sided. You can see that the galaxy is in an asymmetric place, but there's certainly bright emission either side. 7018 is basically of FR2 structure. There are hotspots either side, more or less symmetrical from the core. And at 7017, probably not a very impressive object. There are a few other sources in the field, one of which turns out to be quite interesting, but I will avoid discussing it. Okay, what do we want to do? What we wanted to do was firstly, try to work out why the radio emission that comes out of the north of 7016 appears to stop so asymmetrically, turn around and go back. Second interesting question is, why does an FR2 source like NGC 7018 show such prominent trails? Normally we think of FR2s as having hotspots and nice closed cocoons. The bends in 7016's jets may or may not be associated with the edge of the galaxy gas distributions. We wanted to look for that. And the way of doing all of this was to make a good radio map or series of radio maps and to make a rather better X-ray observation. And this was the better X-ray observation. I've put on here the archival VLA data. What you can see is that a smooth circular X-ray source this isn't. It looks more or less C-shaped. It's got very low X-ray brightness off to the southwest. There's an obvious cavity in the X-ray emission in here, and a bright sort of C shape of X-ray emission that curls around from somewhere near 7016, 7017 through to 7018 and then on. NGC 7017 is well detected in the X-ray, even if it's not detected in the radio, because there's a lot of gas associated with its atmosphere. The typical gas pressure we're dealing with here is something like 10 to the minus 12 pascals. And the region of the cavity has got a pressure which is a half or a third of that. We can tell that both because the density is lower and the temperature in there is lower. The hottest gas lies out here to the northeast and down here to the south. So a lot of X-ray structure, a lot of gas structure, a lot of something is going on. Here's an improved 1.4 gigahertz map made with the VLA. The striking features are what are marked here as the filament and the swirl. The swirl, you can see that the core of NGC 7016 has a bright jet coming out to the southeast, a fainter jet coming out to the north, which then comes up, turns through about 150 degrees, goes into this curious donut-like feature, American donut-like feature, with a hole in it, and then seems to stop on this image. Down to the south, the jet comes out and bends. The bends either side of the core of NGC 7016 are more or less symmetrical, very suggestive of gas leaving a galaxy atmosphere. Out in NGC 7018, we have a nice bright core, nice bright hot spots at the extremes of the cocoons in the normal FR2 galaxy style, and then this curious looking filament that comes out to the west. The source up at the top right in the far northwest is the bonus source, which may or may not be a rather weirdly distorted quasar. I'll pass on from that before I get sidetracked. Here's a 5 gigahertz map I made of NGC 7018, just to convince you that it really is FR2-like. We have a nice bright core, a one-sided jet, very narrow, coming out, bending, and then going up to a double hotspot at the north. On the other side, we get another double hotspot, again, very bright, very compact, at the extreme of its cocoon. The resolution of this image is about 600 parsecs by 400 parsecs at the redshift of Abell 3744, which is more than enough to tell us whether we're dealing with hot spots or just warm regions of increased radio brightness. You can see this rather curious V-shaped structure in the northern lobe as well. Down at the bottom end here, this is reminiscent of an awful lot of high power radio lobes. Nothing very unusual. It just looks like an FR2 radio galaxy. At least it does until you put the 1.4 gigahertz on top. Here's that southern hotspot, and the bright region we were talking about before is down here at the lower left. Then you get this extensive filament field that's drawn out and ends in a peculiar bar structure out here at the end. There's a point-like radio source down at the base of the filament field on the edge of the cocoon. This may or may not be relevant. It is not the second core of NGC 7018. That's a good deal further north and east, but it may have a part to play. We'll talk about that in a bit. So 7018 is clearly an FR2 type radio source. It has the characteristic high brightness hotspots, the characteristic cocoon. It has a characteristic one-sided jet, which just looks like it ought to be relativistic. I haven't got a VLBI map, fairly obviously, but I'm convinced it would be a relativistic object. The outer lobes are brighter than the regions close to the center, again, as usual, if you have a spectral gradient. And we have this very extensive filament field coming out of the southern lobe. There's also one at the north, but that's very much fainter. Curiously, if you really turn up the gain on your imaging, from the bar at the end of the filament field, a very long, thin filament comes out and appears to terminate at about the location of a small radio source. It's as if this feature, which is less than 2 kiloparsecs in diameter and extends around about 150 kiloparsecs in projection, is being drawn out from this bright region at the end of the filament field. So the aspect ratio of that thing is around about 100 to 1. It's mostly straight, but it shows a double bend, and its surface brightness is a good deal higher than the surface brightness of the fairly diffuse radio emission around it. Its energy density is fairly high, therefore. Now, how's it survived? If it's got a high energy density internally, it ought to be expanding sideways unless it's being confined by something. And it won't be presumably extremely fast at this location. The typical dispersion time of something that thin is only a fraction of a few million years. So it's not going to be there very long. Something has got to, if it's going to be inertially confined, it's got to be traveling at something very close to the speed of light, even so far out, and is rather low power. Is it actually a flow structure? Is there any evidence that anything's flowing up that pipe? And the answer is probably no. It could be just a rolled up magnetic filament. And with the presence of the point source at one end, it might be some sort of filament that's being dragged out of the filament field by another galaxy passing through the filament field. And the thought I want to implant is that in a cluster environment, if you have an extended radio source, dwarf galaxies and even somewhat larger galaxies have got to be passing through those radio envelopes fairly frequently. Since the plasma associated with a galaxy is highly conducting, any passage of a galaxy through a radio cocoon or through a filament field is going to require the magnetic flux to become wrapped around the object that goes through the filament or the cocoon. And so you might well end up with something like this sort of structure over a period of a crossing time. And the crossing time for this thing is going to be something like 80 or 100 million years. That would mean that the radio source, NGC 7018, had better be of order 10 to the 8 years or more old in order for something this long to have been dragged out of it. Now, NGC 7018 is not itself at the dynamical center of the cluster, it's going to be moving around. The filament field shows that radio bright plasma and fields are definitely coming out of the radio source. They're flowing in the general direction of the cavity in the X-ray cluster, where we know there's a lack of gas pressure to stop the X-ray emitting gas collapsing. And over about 2 times 10 to the 8 years, at a flow of round about the sound speed in the external gas, it is possible for NGC 7018 to continuously fill up that cavity with radio emitting plasma that could then provide the supporting pressure for the cluster gas. So this may be an example of an extremely large magnetic support and cosmic ray pressure support bubble at the center of a smallish cluster of galaxies. Now, we know there is a lot of radio emission in that region because the overall spectrum of the cluster is quite steep, and there's a lot of missing L-band flux density from single dish measurements. So there is a lot of large-scale emission out there that's worth going to see. Now, if my assertion that this could be a magnetic structure is valid, then a corollary is that you ought to have rather good magnetic structure along the filament. And I'd look for high polarization. Unfortunately, the brightness of the filament is only about 3 times the noise level, and the chance of seeing detectable Q and U in the image that I've got is frankly 0. What's required is to re-image this field now, probably at L-band and S-band, and reaching a noise level of order 5 or 6 microjanskies to get at that polarization. For something like a meerkat, that is now very definitely doable, and is a project that I would certainly urge on the time allocation committee when I get around to writing a proposal, or somebody else if they get around to writing a proposal with me. Here's another very curious structure. This is now NGC 7016. I talked about the bright southern jet and the fainter northern or northwestern jet, which are almost symmetrically disposed coming out of the core and have bends at almost the same distance from the core. Coming out to the western side, the jet seems to come out. It brightens significantly at the bends as usual, but then we have this curious reversal of direction where it inflates something that looks like a mini lobe, but then turns back, and then goes into this strange circular structure. That is very definitely a ring with a high contrast hole in the middle. What is less than obvious on this picture is that that ring is a double-stranded ring. It looks like whatever flow came out of this point has gone around something twice before breaking up. The magnetic field in that ring lies around the ring. So it's as if, again, you've got a magnetic thing being wrapped around a narrow hole. You can perhaps also see that outside the ring, there's this sort of murky area of little filaments which are showing up at an extraordinarily low level, and you wouldn't normally believe. Those form the base of a backflow that flows back to the southwest, the southeast, more or less parallel with the main jet, and constitutes the other part of the radio trail. On a low frequency map, you can see that the overall radio source is considerably broadened in this region by the presence of very steep spectrum emission, which this image isn't finding, which gradually is inflating the well, some sort of region near the main jet. Resolution of this picture, only 2 by 1 arc second. That's about 3 kiloparsecs by 1.5 kiloparsecs. You can see how tight this ring is. Where is it? It's on the edge of the cavity. There is no X-ray emitting gas enhancement in the neighborhood of that blob or the jet reversal blob that might have caused it to reverse. What I was expecting when we started doing this work was that there might be an X-ray enhancement in this region which could provide additional pressure or dynamical pressure that would turn things back. If there is additional pressure that's doing the turning back, it can only be because material in this region, which appears to be of low pressure, is moving quickly. Or possibly what's happening is that this jet flow is being turned back not by colliding with the X-ray gas, but colliding more with the magnetic pressure of the cavity radio source. And it's interesting to note that the filament that comes out of the lobe of NGC 7018, shown in the bright bit here, lies around the other edge of the cavity. It doesn't lie across the cavity at all. So both sources appear to be reluctant to enter the region where we know there's a lot of diffuse radio emission. So just to summarize that, we've got this very sharp turn and then the circular structure. The flow is fairly broad, around 3 kiloparsecs wide. And although it manages to stick together to go around this loop, it then falls apart rather spectacularly into a filament structure. What is doing the bending? Well, it could be bouncing off the cavity material. Another possibility, though, is that a fairly low speed jet, after it's turned once, has now encountered the wake of a galaxy that has gone past NGC 7016 at some time in the recent past. And something like an NGC 7018, which is a big blunt instrument going through the intercluster gas, would leave a significant turbulent wake behind it that could easily provide vorticity on the sort of scale needed to wind up a slowish jet, I think. I just want to make the point that these rings are not that unusual. Here's another one that my student Josie Rawes found in NGC 6109, which is one of the less well-known 3CRR sources. The structure is a bit different from NGC 7016. You again have a one-sided jet, and on the other side, where you can see there is still a counterjet, there is this very nice looking ring. And once again, the jet appears to come out, enter the ring and go round, and then exit in a filament field that is then drawn back parallel to the main jet. Doesn't show up very well on this image, but at a low frequency image, you can see extra emission here. In this case, I think we know what's going on. In this case, it looks to me like the counterjet is encountering the bow shock of NGC 6109 as it goes through the group gas that it's moving through. And if the counter jet hits the bow shock near the apex, the roll flow, the vortex at the head of the apex, is going to wind it up and break it up in the sort of way we see here. Although I'm not showing it, there's a very strong rotation measure structure associated with this and quite high local polarization. A few more words on that X-ray cavity. Its maximum lifetime is around about 100 megayears. The external pressure, about 10 to the minus 12 pascals. You can support it by radio emitting plasma. And that is particularly easy if the material has got a very steep spectrum, because then you've got a lot of very low energy electrons and they provide most of the pressure. The surface brightness is much too low to see in our high resolution map, though it makes about a 50% contribution to the NVSS flux density. We think we might have seen an indication of its reality and the reality of the pressure it's providing, though, through its inverse-Compton emission. The X-ray spectrum of this part of the cluster is not a very good fit to a pure thermal spectrum. It appears to have a power law component that's consistent with some inverse-Compton emission also occurring there. Returning to something I said a little bit earlier about unregulated heating causing mass ejection, if we go through the dynamics of the galaxies and look at the hydrostatic equilibrium or even moderate departures from equilibrium of the gas in the cluster, we come up with a baryonic fraction out to R500 of around about 0.07, which is about half the cosmic baryon fraction. So about half the baryons you'd expect to find in this group or cluster have been expelled beyond R500. And this may be an indication that we're seeing the cluster in an unusual dynamical state, either because of current excess heating from the radio source or a current merger, or both. Okay, I'm going to switch gears and talk about a brightest cluster galaxy instead of an overall cluster. I'm going to talk a little bit about Holm 15A, which is the brightest cluster galaxy in Abell 85. I've shown on the left here the X-ray image of Abell 85 from Ichinoue et al. One very bright cluster, several subclusters dropping in, and on the right an optical field, which as usual is fairly uninformative, although it definitely shows you that the brightest cluster galaxy in Abell 85 is an extremely dominant structure. It is very much brighter than anything else. The curiosity about that brightest cluster galaxy is that it has a very large optical core. Normally, the centers of bright cluster galaxies have got fairly peaked brightness distributions, but this one's got a very flat brightness distribution. So something has been going on in the center of the galaxy to cause the distribution of stars to be flattened out rather than to be a bit cuspy. That sort of effect can happen if there's been a recent merger, but it can also happen if the stars near central orbits are being pumped out in angular momentum by two big black holes orbiting one another. So we imaged this well, with a number of optical telescopes, but also with the VLA, to see if we could find evidence for two small radio sources towards the center of the galaxy that might be associated with supermassive black holes, which are in orbit and whose orbital motion is pumping out the core radius. Well, here's what we found in this object. It's a very weak radio source. It's about 2.5 millijanskis at 8 gigahertz or 10 gigahertz. The core dominates, it's about 1 millijansky. And the core has got a relatively flat spectrum, quite nice, pretty normal. The extended emission near it has got a spectral index around about 1.8 and has this odd loop-like structure on one side. No hotspots, no evident jets. This thing to the western side is more like a bar than a jet, and again is very steep spectrum. Its spectral index is about 1.8. The resolution of this image is around about a quarter of an arc second, corresponding to something like 300, 400 parsecs. This is also associated with an H-alpha nebula. Here's an H-alpha picture that is hot off the press. In fact, it's so hot off the press that I didn't have time to correct the typo in the attribution at the bottom, so apologies for that. This only came in yesterday. The radio source is not symmetrically distributed in this H-alpha. It lies down here and appears to be pushing on the gas field that we're looking at in the H-alpha emission. The core of the radio source, although it doesn't coincide with the center of the H-alpha, is very closely aligned with the centroid of the optical isophotes of the galaxy. It lies within about 50 parsecs of the optical centroid. The typical lifetime you'd expect for gas like this at the center of a galaxy is only about 3 million years, based on the sound crossing time. So what's going on? Well, yeah, I don't know. The radio emission is very steep spectrum. It's much more like a supernova remnant than a normal active galaxy. But it has this very compact core, as if there is a supermassive black hole in there. So this might be something caught at an ephemeral phase when the active galaxy is turning on. We don't see any detectable emission on scales much outside that picture at 1.4 gigahertz. There is no sign of polarization in that structure at all, even where the signal to noise is in the hundreds. And as far as the energetics of the source goes, because this is very steep spectrum, it's a little bit hard to be sure. The estimate of the internal pressure, the estimate of the energetics depends critically on what the minimum electron energy associated with the source really is. What we can certainly say, though, is I can't see another point source in the immediate neighborhood of the core, which could be the second supermassive black hole. The only possibility is this object out here that is too far out to have a significant effect. I was looking for something closer. As to what's creating this morphology.
Excuse me, Mark, I'm sorry. Can we please turn off our microphones? Please, can everyone? Thank you. Sorry, Mark, please. Yeah.
That's okay. It sounded like one of my classes. What's creating the loop, that is an utter mystery to me. Whatever it is, it's unpolarized. Possibly because of depolarization by the H-alpha foreground. Now, the sort of estimate of pressure I come up with is around about 10 to the minus 11 pascals, which is a conceivable pressure for the center of a bright cluster galaxy like this, where the density is high. The temperature of the gas isn't that enormous, but it can certainly provide a sensible amount of pressure. There's no indication of supermassive black hole binary stirring. And if this AGN was offset from the center, the orbit period that we're talking about is only about 100,000 years. So what to say, I don't know. Certainly the hypothesis that there might have been a binary supermassive black hole in there is not supported, but I wish I knew what was creating that loop structure and why we have such a steep spectrum. It's like there's leakage of old electrons from what wants to be an extremely compact object, possibly an analog of one of these compact steep spectrum sources that people find at rather high powers when they look at compact steep spectrum quasars. Second example that we looked at in the same project is in Abell 1775. This has another very large core, and it is another bright X-ray cluster. Here, a cluster which is obviously undergoing considerable merging. You can see from the X-ray image here, just from a recent paper by Bottillon et al., that there's a lot of X-ray gas substructure. Bottillon et al. Concentrated their work on a very long trail source that's associated with one of the bright galaxies at the center of the cluster. Being a little bit weird, we didn't work on the bright one, we worked on the faint one. And here's the faint one. The total flux density here is around about 2.5 millijanskis, and it's a boring, ordinary looking radio source. It's got a nice core, and that core is coincident again to around 40 or 50 parsecs with the center of the brightest cluster galaxy. Nothing very much I can say about this. The resolution here linearly around 300 parsecs. So we're certainly looking at a small radio source which lies entirely in this image within the gas envelope of the galaxy. An interesting question then is, why is it so distorted? Because the time scale for the inner part of the gas in a galaxy to settle is quite short. And even if this galaxy was moving quite quickly relative to the intercluster medium, you wouldn't expect the wind to penetrate that deep into this dense an atmosphere. But nevertheless, we've got quite strong distortion. Here's the overall field. The source we're interested in is this one, and there's the base of the very long radio trail source that Bottillon et al. Are looking at. The core is down here. It's an extremely bright bent radio jet that becomes very distorted, presumably because this galaxy is moving very rapidly through the general intercluster gas. Much of the older imaging confuses this source with this very much brighter source, or loses the integrity of this source. And I want to close by showing another very well-known radio source. This is 3C83.1b, NGC 1265, a very fast-moving, well-known head trail source in the edge of the Perseus cluster. The galaxy is down here. On this scale, it's about this big. And it's moving towards 3C84, NGC 1275, which is in the direction of all these rays, which are artifacts from the LOFAR imaging that's being used to make this picture. The features I want to point out, here's the usual radio trail, are this strong loop to the west side of the trail, and this very much larger radio source that has filled out the volume to the north and east of the main radio trail. Because the volume of that is so large, the energetics of the 3C83.1b radio source go up by a significant factor if you believe that the steep spectrum electrons that are emitting this continue to reasonably low energies. This is a preliminary version of a map that Emmanuel Bempong-Manful and friends are currently preparing for publication. I hope that's going to hit the MN display region fairly soon once he's finished writing his PhD thesis. He'll be working for SKA starting in a few months' time. This bright region at the northeast is the old anomalous tail dating back to 1979 and a paper that I wrote back in 1980, which gives you some indication of how long I've been doing astrophysics. Okay, let me wrap up there. Some take-home messages. First thing, so there are some surprisingly strong source distortions out there, rings. And I've shown you rings in two objects, NGC 7016 and 6109, and a loop even in a brightest cluster galaxy. That was the brightest cluster galaxy of Abell 85. What is producing those loops? Well, it can't be the same process on all of those scales. The cluster scale cavity in Abell 3744 is plausibly filled by radio emission from, radio emitting plasma that's been lost by the cocoons of NGC 7018 and possibly its friends. And it appears that those cocoons can be punctured by galaxies going through them, so that what would otherwise be well-contained radio plasma can leak out, as can magnetic field, into the wider environment. I showed you the 3C83.1b image, this sort of phantom radio lobe that lies out to the east. It's not entirely clear whether that actually originates in 3C83.1b or is an older piece of radio plasma that's been reinvigorated by being hit by 3C83.1b, because that is moving supersonically, at least twice the speed of sound, in the edge of the Perseus cluster. And I regret to say that our look for binary black holes, which happen to be radio sources in these few brightest cluster galaxies, has failed. But we plan to keep on trying. And I'll leave it there. Thank you very much for your attention.
Many thanks, Mark. Thank you for this wonderful trip through these galaxies and their peculiar, I must say, radio structure. So we have the questions. Yes, if anyone needs to ask a question, please raise your hand. So I can see a hand from Bowmans. Please go ahead.
Hi, Dominic Bowmans from Bochum University. I was very intrigued by the Abell 85 source, which you show, where you showed the radio emission and the H-alpha emission. So I don't recall exactly the scales for both, but the loop in the radio emission is in the south, the loop or in the H-alpha emission is in the north. So would the radio, the H-alpha emission all foreground, or would they be intertwined? And then it would be interesting if the radio, the relativistic plasma is, well, shifting away the thermal plasma in the X-ray, in the H-alpha emission.
Yes, I'm not yet sufficiently convinced of the Subaru astrometry to be able to tell you for sure, but it appears that the brightest part of the H-alpha is offset by about a kiloparsec from the brightest part of the radio emission. So I think the radio emission is more to the side of the H alpha than embedded in it. Now, I would be more definite about that if we had any polarized signal that I could do a rotation measure analysis of. Yep. Because even though this is a 3 microjansky noise map, even with that, I can't see detectable polarization anywhere in this source. And that's anywhere. So it's completely depolarized.
That's indeed. Okay, thank you very much.
Many thanks. Anyone, any other question from anyone?
Can I ask a question?
Yes, absolutely.
Sure.
Yes.
Is that you, Bernard?
Yep.
Seems to have frozen.
Yep. Okay, let's wait then. Let me also. Seems to be frozen. Okay, let's wait and until we do that. Maybe I can also ask a question. I remember, I don't remember exactly the name of the system. It was from one of your students, NGC
6109.
the one with the circular. Yes, 6109. Yes, thank you. Exactly. So can we say that this naively now, this circular donut-style radio structure is caused also by a kind of a different kind of backflow, or it's just only based on, let's say, magnetic? I mean, how can we, terminology-wise? I mean, is it something close to that, or?
I think, well, there's got to be a magnetic component to it. It's quite highly polarized, but fundamentally, NGC 6109 is a high-speed member of a group of galaxies and is traveling probably at Mach 2 or more through the atmosphere of that group. That means it's going to have a quite strong bow shock. And if the jets happen to be aligned so that one of them lies near the apex of the bow shock, when it hits the bow shock and wants to penetrate, it's going to be fighting against a compression which wants to turn it backwards.
Yeah.
Now that structure is what an ex-student of mine called Shandor Molnar asserts is capable of producing this, but it requires quite an interesting coincidence. You have to have the jet oriented at the apex to a fraction of the jet diameter at that location. Now, we may be assisted in this particular case because that's the counter jet. So it's the jet that's pointing away from us. So the linear scale of the jet is not quite what we're seeing by relativistic effect. But as you can see, the bases of the jet show a jet counter-jet ratio, which is quite high. So this is something that really looks like a significantly relativistic injection down the bottom there. By the time it gets out here, it's much more symmetrical. Curiously, also, the jet counter-jet ratio, either side of the base, is consistent with this feature being the same distance from the core as that feature. in terms of time since ejection on a fairly, well, roughly, let's say it roughly, if you do a rough dynamics calculation. The difference in their apparent positions is just due to relativistic foreshortening.
Many thanks. Yes.
But there,
So,
again, there's no
Yeah.
gas there that shows up as an X-ray enhancement. There's no gas there that shows up as an optical line emitting gas. There's no dust feature that shows up there. And this is unlike another object that Josie mapped, NGC 7385, where there's a very definite gas and dust structure that's being struck. And in that case, we can associate free absorption from that gas and dust with rotation measure from the same gas and a distortion of the jet from the same gas. And everything works quite nicely.
Yeah, sounds, very interesting. Many thanks. Anyone else? Any other questions? Please raise your hand or just pop up. It seems that Bernard is offline. Fortunately, we must have missed this question.
Well, let me just interject that it's nice to see some familiar names from the old DARA project showing up on the participants list.
Yep. Yeah, it's nice to, Ewan, All right, so if nothing else is there, let's thank our speaker. Thank you very much, Mark. It was a great pleasure having you today and showing all these extremely interesting new radio structures. So,
well, let's hope that in a few years, when SKA version 1 is up and running, we can start to do a better job.
Yeah, exactly. Yes, hopefully, yes. That's great.
Okay, good to see you all, and see you somewhere sometime soon in the flesh, I hope.
Exactly, yes. Thank you very much, and thanks everyone. Yeah.